I'm sure it's been fascinating to see all of the AI algorithms, and all their capabilities. And it's easy to forget what has made all those algorithms possible is the constantly improving capabilities of the hardware that powers them. And a significant component of that improvement has been coming from something called Moore's Law. I'm sure you've all seen graphs of Moore's Law. I'm going to save you from having to see one, but I will present evidence that Moore's Law is over. And that is fundamentally because Moore's Law was an economics law, and specifically, it talked about the exponentially decreasing cost of transistors. And while actual transistor costs tend to be a closely guarded secret, there is evidence that they're not going down, as shown in this chart, which is showing gates, which are small collections of transistors. And what we see is that Moore's Law is flattened out. The response has been a focus by computer architects to use specialization to create more efficient accelerator architectures. And I participated in that. And here is a subset of the accelerator designs that I've worked on over the past few years. Each has unique attributes and capabilities, but like most accelerators, they tend to be described by pictures like this, which are somewhat inscrutable, and long natural language descriptions that tend to be incomplete and, even worse, lack structure. That makes it difficult to be able to separate the big picture from the details. To improve the situation, I suggest taking inspiration from the world of science, where it is generally accepted that science advances by systematizing and categorizing knowledge in the world. And I agree with Nobel laureate Herb Simon, who sees many parallels between science and engineering. And so one might assert that engineering advances by systematizing and categorizing knowledge about designs. To apply that to AI accelerators, we note that a commonality amongst many of the algorithms is that they can be expressed as tensor computations. So what's a tensor? Well, tensor is simply a set of values organized into a multidimensional structure, where we will call the dimensions ranks. So we have a rank 0 structure, rank 0 tensor, which is just a single value. We have a rank 1 tensor, which is an array of values, and so on. And the other thing that's very nice is that there's a very nice way to represent a tensor. So we have the tensor A, I, J, K, where I is the row, J is the column, and D is the depth of a tensor A. However, to systematize things a bit and avoid dealing with the myriad of different concrete ways that people represent tensors, we're going to use a single abstract representation, which we call the Fibertree. In this abstraction, the tensor is represented as a tree. Here, each level of the tree corresponds to a rank. Each row or column in the tree, in the tensor, corresponds to what we call a fiber. And each fiber is indexed by a coordinate. And then finally, each point in the tensor is identified by a path of coordinates through the tree. I've illustrated a dense tensor, so there is a non-zero value in every point. However, many problems are sparse, meaning that they have many zero values. Why do we care about this? We care about it because there are many opportunities for exploiting that sparsity. In specific, if the tensor is sparse, it can be compressed, taking up less space. And using these simple arithmetic expressions, we see that having a 0 means that there's really nothing to do. And so an architecture that can exploit these characteristics in sparse operands can result in savings in storage, execution time, and energy consumption. To include this information in our data abstraction, we return to our Fibertree and note that if the tensor is sparse, like this, then we can simply remove coordinates and their children in the tree. So now turning to the computations on these tensors, there's actually a very nice notation for describing the essence of those computations. This notation has its origins in a paper by Albert Einstein over 100 years ago and is referred to as Einsums. Here's a very simple example of matrix multiplication in this notation. Note how the formula is simply references to the points in the tensors. So it's very simple. So how do we interpret this Einsum? We interpret the Einsum by saying that what we're going to do is traverse all the points, in the space of all legal values. This is referred to as the iteration space. And at each point in the iteration space, we're going to calculate the value on the right-hand side. We're going to then take that value and assign it to the operand on the left-hand side, unless there's already something been assigned there, in which case we're going to reduce the value into it. Notice how the Einsum does not specify the traversal order. So what it's really doing is saying what the computation is, but not how to do it. The Einsum also tells us a lot about the work that needs to be done. Here's an example. When we have a situation where the same index, in this case k, appears in both operands, sparse operands, we need to get a value from each of those operands. We call these shared indices. And in order for there actually to be any work to do, both of the operands must be non-zero. What this corresponds to is an intersection. And what we have found is that this and many other operations that are implied by calculation of the Einsum correspond to manipulations of fibers in the Fibertree. So for intersection, if we have two sparse fibers, what we notice is that these two sparse fibers only have coordinates, common coordinates at 2 and 8. And so the result of the intersection is a fiber with only coordinates 2 and 8. There are many hardware implementations of intersection, but what we have done is separate out the semantic requirements of the calculation from the details of the design. With that knowledge, we have found that what we can do is very concisely express the essence of many published design, breaking it down into the Einsum and the traversal, which we call the mapping. But now, with a concise and comprehensive design specification, there's a number of different things that we can do. One is build a model to characterize a design. Such a model takes in the Einsum, the traversal information, and design details, and can generate speed, area, and energy. But these ideas can also help with design. So a student took this accelerator design that was published and studied this diagram from the paper and looked at the long English natural language description and actually found that that wasn't complete, so contacted the author and found out the remaining details, and with that information was able to write a comprehensive, concise, and complete description of the architecture for that accelerator, which she looked at and said, oh, there's some very obvious optimizations here, and wrote them down and generated dramatically improved performance. So in summary, I would argue that taking this approach allows for implementation-independent expression of computations, format-agnostic specification of processing activities, descriptions of accelerators that are decomposable into separation of concerns, concise, precise, allows for the creation of analytic and more detailed performance models, and provides a path for exploring the new architectures that we're going to need in the future. Thank you.